And we uh, saw a few other things as well. Most important concept we saw was of the zero crossing theorem. So we saw some eigenstates of this particular problem, some energy eigenstates of this particular problem. And they are basically, there'll be some E1 and there'll be E2, E1, E2, and so on, right? So these are the energy eigenvalues. And for each of these energy eigenvalues, there's going to be some corresponding energy eigenstate. So it looks something like this, right? So energy eigenstates and eigenvalues. And yeah, before this, we did the same for a completely free space, right? Blank space. There is nothing. Fully free space. And so pretty much now what you should realize is, in any particular problem in quantum mechanics, what is it that we really do? What we do is we just specify the u as a function of x and seek all the energy eigenvalues and the corresponding eigenstates. This is what we seek. Typically, this is what we seek for a trapped problem where we want to know about trapped states. And in some problems, we have unbound states. We have basically propagating states. And in such problems, we are looking for calculating scattering probability, scattering amplitudes rather. So we have two kinds of problems in quantum mechanics. One kind of problem is where we have, so in both, anyway, you have to specify a potential. Once you specify a potential, I will tell you, well, once you specified a potential, two kinds of states are possible. One kind of state is a trapped state, and the second kind of state is a propagating state. Trapped state usually has discrete eigenvalues, and propagating states usually have a continuum of eigenvalues. And in trapped states, what we are interested in finding is how many trapped states are there, what are their eigenvalues, and what are their eigenstates. In propagating state problems, what we are interested in is what are the different scattering probabilities, right? So any problem in quantum mechanics, pretty much that what you will encounter in all kinds of semiconductor physics devices, even most of solid state physics, really just boils down to these two kind of problems. So we're going to do a time independent Schrodinger's equation, specify a potential, then see what are the possible trapped states, what are the possible free states, and then we see, okay, are we interested in more of the trapped situation, or are we interested in the free scattering situation? Some problems you might have to deal with both at the same time, right? And this is pretty much every problem that you see in quantum mechanics is going to be just like this. Especially for, I wouldn't say in quantum mechanics, I would say in semiconductor physics, will be pretty much this, right? Now we have done a one-dimensional potential and we have solved the Schrodinger's equation in a, even the wave function, everything we have assumed as a one-dimensional problem. That part will change. Eventually you will go to two-dimensional problems and even three-dimensional problems. But anytime you see a three-dimensional problem or a two-dimensional problem, not to worry, right? I mean, the mathematics will become very complicated. You have very complicated differential equations. You have special functions of differential Bessel functions. hypergeometric functions, what all things will come. Doesn't matter, right? At the end of the day, this is what we are doing. Maybe you are doing it in a more complicated um, coordinate system, like a 3D coordinate system. Um, One more advanced step compared to this is time dependent Schrodinger's equation. Solving that in one dimension is itself a little complicated. We don't need that for semiconductor physics. You need it for doing optoelectronics because there you have transitions, right? So you need it for that. All semiconductor device quantum mechanics is pretty much ground state, right? These are all ground state kind of problems, which means everything will be in the ground state. There's no excitation between states and so on. For those things, you need time dependent Schrodinger's equation. But in semiconductor device physics, it is definitely in semiconductor, definitely also in this class also, we don't really need time dependent Schrodinger's equation. Okay, so I hope it is you have a clear idea now of if you open any quantum mechanics textbook, what exactly you're going to find. Basically, what you're going to find is you're going to start from this very simple potential u of x is 0, and then they go on to more and more complicated potentials. They go to infinite well, and then they go to a finite well, then they go to one-dimensional wells of arbitrary shape. Okay, so for example, here we have a rectangular shape, right? You can take, I don't know, some shape like this, for example. Or you can take a quantum infinite well and apply an electric field, right? All such kind of things, we just keep on adding more and more complexity to it. But at the end of the day, you have to understand that there is something that is happening in real life, right? Real life is we have atoms, we have collections of atoms, and we are interested in understanding what is the property of an electron in such a situation. And so your first job is to construct a good enough u of x. Okay, this is turns out to be very hard. So initially, we specify arbitrarily, right? We say, oh, imagine a square well, imagine this kind of a well, and so on. Those are really toy problems. Okay, if I ask you where is infinite well in real life, it's not there, right? And if I ask you where is a finite potential well, square shape, it's not really there. Okay, but a similar kind of object is there. An atom, for example, its potential is going to be something like that, right? And it's in 3 dimension, so it almost looks like so that is why this is very popular. So when we solve the infinite well problem, you're not solving just a toy problem, but you're understanding all kinds of systems in which an electron is trapped. And what is the system that we are very familiar with, where an electron is trapped? It's the atom, right? So people took the Schrodinger's equation, they first solved it in a infinite potential well, where the mathematics was easy. Then they moved on to a finite potential well in one dimension. Then they understood that. Once they understood that, then they said, okay, now I really understand finite potential wells, how the electron behaves, right? We also understand it. It has some eigenvalues, it has some, distributions and so on. We know that. Then we move on to the atom. And when physicists did that, they were able to, in fact, first they solved it for a hydrogen atom, which is simplest. There's only one nucleus. And when you write down the Schrodinger's equation in a hydrogen atom, it is actually a partial differential equation in 3 dimensions in spherical coordinates, right? R, theta, phi. So that equation solving becomes a little bit difficult. So that's why I'm not going there. But there also you'll have different eigenstates. So you might remember, SPDF quantum numbers are there. And if S equal to 1, we assign these numbers, right? And then we have different kind of orbitals. Those are just your eigenstates. Whatever we have done, these kind of green things that we're drawing, just drawn in a three-dimensional space. That's it. Okay, that's all there is to it. Then once you so after infinite potential, well, go to a hydrogen atom, you understand the quantum mechanics of the hydrogen atom. Once you understand that, then the question comes, okay, now let's go to a slightly more complicated atom, helium, for example. Again, it becomes very difficult because there are two electrons. How do the electrons interact with each other? And people did not, had a hard time with it. Then they realized, we can simply subtract the first electron, combine the first electron with the nucleus, and then solve for the outermost electron, just like we solved for a hydrogen atom. That worked out well. So for the valence electrons that are on the outermost orbits, you can still use your understanding of the infinite potential well. You can get some idea. The electrons that are inside, now those are slightly harder to solve for. You need slightly more clever mathematics. In fact, it's called the tide binding models, right? You might have heard of tide binding models. So you need slightly more complicated. I'm not going to go too deep into it. What I want to just tell you is that the trick there is to choose this potential in a clever way. You don't use the real potential, you use something called as pseudo-potential. So anybody who's going to use quantum espresso and other softwares might have heard of this term called the pseudo-potential. The pseudo-potential is basically a trick used for solving the Schrodinger's equation in atoms other than hydrogen, where there are more than one electron. Remember, all the Schrodinger's equation that we have is simply for just one electron, right? So one electron wave equation, basically. So in real life, of course, we don't have one electron wave functions, right? Ideally, they're more complicated. So how do we extend the machinery of one-dimensional Schrodinger's one electron Schrodinger's equation, not one dimensional, one electron Schrodinger's equation, to situations where there are more than one electrons? That is done by this tool called the pseudo-potential. And there are softwares, you might have heard about it, called Quantum Espresso, where you can calculate the band diagrams for different crystals. You can calculate effective masses, you can calculate densities, you can do all kinds of first principles atomistic simulations, right? There, this is the way to do it, using pseudo-potentials. Okay, so very, very fascinating field. I'm sure if you people continue to work in this field, at some point you're going to end up using quantum espresso. And there, if you encounter this pseudo-potential, nothing to worry, right? This is all that's happening. We are trying to stretch whatever we know about a one electron quantum mechanics to a situation where there are definitely more than one electron. And that's what it's all about. Okay. So going from this infinite potential well, very simple model, I told you how we can understand a lot of things that we see in the universe by starting to solve quantum mechanics, Schrodinger's equation, one electron Schrodinger equation in atoms. And this leads into quantum chemistry and all these kind of very interesting things. However, we don't have time to go into that jungle here, so I'm going to stop this discussion. But I'm going to continue, however, by doing a one-dimensional finite well problem. This problem we started doing last time. It cannot be solved analytically at all. Okay, so I cannot solve it just by algebra in entirety. It has to be solved numerically. But we will set up the problem first. When we set up the problem, even without solving it fully, you learn a lot about wave functions and so on. And this is a prelude to why tunneling happens. So if you understand this, then you'll understand tunneling much deeper way. Okay, that is what it is. So now we will go into the mathematics of this. So look at the geometry. First, we draw the potential u function. This is u of x. And we have to choose the geometry properly. So because there is a symmetry, there is an inherent symmetry in this problem. Symmetry about the center of the well. We did not need this in the infinite well case. But here it's more helpful. So I'm setting x equal to 0 to the center of the finite well. Right? That's it. So now we will, without solving the equation, let us think about a few things. When we solve the equation, we're going to get some function phi of x, right? Even without saying anything, we know that the probability of locating the electron at x equal to -1 should be equal to the probability at x equal to +1, right? So we can conclude that mod phi x squared must be an even function simply by physical symmetry. Great. Once this is true, if square of is an even function, then there is two possibilities for phi of x itself. If phi of x square is an even function, phi of x itself can be an even function or an odd function. It cannot be anything other than this. It has to be either an even function or an odd function. There are functions which are neither even nor odd, right? It cannot be that. It has to be even function or an odd function, right? Then the second thing we know, this is something, so we are already judging the solution before solving it, right? So we expect these things to hold true. So whatever solutions we get, they have to be even or odd functions. Great. So then you ask, then second thing we know from the zero crossing theorem, that the first solution should have 0, 0 crossings. Second solution should have 1, 0 crossings. So based on that, immediately we can now conclude that the very first solution, or phi 1 of x with an Eigen energy E1, this has to be even. Okay, because if it is odd, only then I'll have a 0 crossing, right? The first one doesn't have a 0 crossing. I cannot have an odd function with with no 0 crossing. That's not possible. So immediately I can conclude that the very first Eigen function.
Sir,
Yes, sir.
can you explain more this thing with even for energy even phi x even?
Yeah. यहाँ तक आपको हो गया ना कि probability should be an even function.
Yes, sir.
So if probability of something is even, this also you agree, right? It has to be either
Yes,
even
sir.
or odd.
Yes, sir.
Okay. All right. So if you draw an even function, we know the. Do you remember the zero crossing theorem? What does zero crossing theorem say? That phi 1x must have no 0 crossings.
Yes, sir.
Do you remember?
Yes, sir.
Phi 2x must have 1 0 crossing. Phi 3x must have like that. ये किया था ना?
Yes, sir. Less than 1. Phi 3 then 2 0 crossing.
हाँ, समझ गया. Okay. So phi 1. So I cannot have an odd function, right? Without any 0 crossing. Odd function has to have 1 0 crossing, right?
Oh yeah, yes, sir.
Okay.
Yes, sir.
Yes. Okay.
Thank you.
Yeah, thank you. Any other question? Okay, great. Right. So E1 must be an E1, the first eigenstate must be an even function, right? And the second eigenstate must be odd. Why? Because I told you, right? It has one crossing right at the center. Because it's we know that phi 2x must be symmetrical, and it should have 1 0 crossing. Then the 0 crossing has to occur at the center, because of those constraints. So we know that phi 2x must be odd. Similarly, you can continue arguing, and you'll realize that phi 3x must be even, and phi 4x must be odd. Okay, you can go on like this. You can continue arguing like this, and you'll realize that this is the case. Great. Okay, so we have already realized all this even without solving anything. And other condition is that whatever final answer we get, it should be continuous, as well as its derivative also must be continuous. So only those kind of functions are possible. Okay, so which means can you think of an even function which I'll draw one even function, okay, whose derivative is also continuous, and you will guess that it should look something like that. Okay, because it has to be trapped also. No, this cannot increase. We know okay, that is a third constraint. Third constraint is that the probability of finding the electron must decrease as x as mod x increases. So the farther we go away from the well, probability of finding the electron must decrease. So if I put all these constraints together, then even without solving, you know that okay, it should look something like that. Phi 1x should look something like that. Phi 2x should look something like this. Phi 2x should look something like that. Phi 3x should look something like, should have three crossings, right? So should do something like that. Okay. So all this we judged based on simply thinking about the symmetry. Now, what is the exact mathematical form for these particular functions? That we'll have to solve by the Schrodinger's equation. But whatever it is, the derivative, slope of the derivative has to be continuous everywhere. Okay, I cannot have undefined slope. It should be a smooth function only. All right, right. So this is what we know. Now we write down the Schrodinger's equation, and we can say the following, that the wave function must satisfy this equation, right? So u of this equation, and when we know that for mod x less than or equal to a by 2, where a is the width of the wall, u naught is 0, u of x is 0. So inside the well, it should satisfy this differential equation. Outside the well, it should follow this differential equation. And whatever solution we get here, and whatever solution let's say I get some solution here, phi 1, I would say phi single dash of, and here I get phi double dash of. These two, there has to be continuity and continuous differentiability. Those are the two conditions, right, between this solution and this solution. So in general, now whenever you do quantum mechanics, this is exactly how they do it. So you impose a potential, then you impose the boundary conditions on it. And this is the procedure that we're going to do in this class, right? So let us now have a look at these equations. This particular second equation is easy to solve because we already know how to solve it. We've already solved it, right? It's just the Schrodinger's equation in vacuum only. So I know the solution must be a. So let me write that solution finally here. I know that phi of x must be a into e to the power jkx plus b into e to the power minus jkx, where k is root of 2me by mod h square. I know this to be true. This has to be the case for x is mod x is less than or equal to a by 2. No doubt here, right? If you now look at the equation for the wave function outside the wall, the only difference is instead of minus e coming there, you have a plus u naught minus e coming here. And remember how we solve the equation, right? We would write d square of phi plus u naught minus e into phi is 0. This is your equation. So d is plus or minus square root of u naught minus e. And we know that e must be less than u naught. So we know that, so this solution is e to the power plus kappa x c plus d into e to the power minus kappa x, where kappa is square root of 2m u naught minus e by h bar squared. Okay, and this is positive. Kappa is a positive number. So we know that the solution has to be of the form c into e to the power plus j kappa. Notice the difference between k and kappa, plus d into e to the power minus j kappa x. This is how it should be for x greater than a by 2, basically. Mod x greater than a by 2. But we can do even better than that. Something we know from physics of the solution is that as x tends to minus infinity, we know that phi of x must tend to 0. So if I put here, if I put minus infinity, then see kappa is positive. If x is minus infinity, then the first term is okay, but then the second term, e to the power minus jx, x is also negative, kappa is positive. So, oh, my mistake, sorry guys, there's no j here, okay? Minus kappa x plus kappa x. Because kappa is root of 2m u naught minus e by h bar square, right? A kappa is positive. Okay, so these are exponentially decaying functions outside the wall. That's what I'm trying to get at. But to the left of the wall, we know that the wave function decays, right? So this is so this c has to, so to the left of the wall it should be of this form only. Okay, otherwise it will wave function will blow up. So it should be of this form for x is less than minus a by 2. So it's so it is something like that. Okay, if you have the other one, then it's going to go up, so that's not possible. So similarly we can write this as e into e to the power, maybe I'll use c here, okay, not c into e to the power minus kappa x for x positive, for x is greater than or equal to a by 2. Okay, so this is how my function is going to look like. So let me write it properly first, just to, so I'm going to introduce two constants. One is this k, small k. This is root of 2m e by h bar square. And I'm going to introduce a number kappa. Kappa is root of 2m u naught minus e by h bar square. Note that both k and kappa are real numbers. They're real numbers. Okay. We consider our zero level to be the bottom of the potential. That's why these are real numbers. Okay. And in terms of this, I can write my wave function as phi of x is d into e to the power plus kappa x for x is less than minus a by 2. Can you see the screen?
Yes, sir.
Okay, there's no problem, right? Okay. And it is c into e to the power minus kappa x for x is greater than a by 2. And it is a into e to the power plus jkx plus b into e to the power minus jkx for mod x is less than or equal to a by 2. Okay, we can do even better than this. We can do even better than this. So let us impose now the condition. Let us have write separately for those the even solutions, and let us write this for the odd solutions separately. For the even solutions, we know that we can write it in the following way. This and this must be same, right? So is equal to e to the power plus j kx. B e to the power minus j kx. And what will happen to this particular term? We need to choose something that is even, right? So we know that this and this will give cos, right? Cos or sine, right? When you add them, but we need only even function. So we can conclude that it should be cos of something. So we know that it should be some constant into cos of k into x, cos kx. Okay, I'm going to call it a into cos kx. And for the odd one, it should be a into sine kx. How can I prove that? You can do that by taking this particular function here and requiring that phi of x must be equal to phi of minus x, or requiring that phi of x must be equal to minus of phi of minus x. Then immediately conditions on a and b will tell you that either a has to be equal to b or a has to be equal to minus b. When a has to be equal to b, then you get a cos kx, minus b, a sin kx. Okay, I hope this is clear to you. Then outside, I should require that it should be d into e to the power plus kappa x, and on the other side should be d into e to the power minus kappa x. Okay, note that those constants should be same, right? If it's even. If it's odd, then it should be the other way around. This should be d into e to the power plus kappa x. This guy will be d minus d into e to the power minus kappa x. So even solution, odd solution. I hope this is clear to everybody, right? Always make sure you don't confuse this little k and capital K. That's very critical, right? They are different numbers. And now we require differentiability and continuity of differentiation, right? We have already used the symmetry portions here. So there are two unknowns. Okay, so we have a is unknown, d is unknown. Now, unfortunately, we cannot completely reduce the other unknown. One of the unknown has to be reduced using normalization, right? So we only have one unknown basically. In this entire function, there's only one known. Why? Because normalization will give you another equation. So one is normalization, another is your boundary condition. Using those two, we can explicitly specify both these constants. There are only two unknowns are there. We have used the fact that odd is there, even is there, right? So we have used those. So basically, two unknowns. Actually, only one unknown by boundary condition, another unknown to be determined by normalization. So let us impose the condition. So condition imposing will tell me that a cos of k at plus a by 2 must be equal to d into e to the power minus kappa times a by 2. This is from the continuity condition. I'm only going to solve it for the even states. I'm not going to. You can solve it for this. Okay, I'm going to solve it for this case. This is a continuity condition. And then the differentiability condition says that minus a sine of kx into k must be equal to kappa into d minus kappa into d e to the power minus kappa x. And at the value a by 2, so I get after taking the minus, I give me a sine of k into a by 2 into k must be equal to kappa times d e to the power minus kappa A by 2. So I have these two conditions. So this is coming from no, this is actually the continuity of the derivative, right? Derivative continuity condition. Equation 1 and equation 2. You got a slightly different equation for the odd states. Okay. Yeah, so I'm going to simply now divide 1 upon 2. So let me move this guy up here. Right. So these are our two equations. Let me just do 1 upon 2. When I do 1 upon 2, I get, or maybe let's do 2 upon 1. Okay, so just for tan of Ka by 2 into K is equal to kappa is equal to kappa, that's it. Or tan of K into A by 2 must be equal to kappa by K. Okay. So now we will express this equation. This equation is what? This we get from the condition that derivative has to be continuous and so on. So this doesn't help us to solve for both, right? It only helps us to solve for one of them. Then it basically it only helps us to give the relationship between D and A using this method. Then after that, you have to use the normalization to give you the value of constant. So that is less important. So we'll not go into that. But let us examine this particular condition here. What exactly is happening here? So I'm going to substitute the value of kappa and K here. This is root of 2m E by mod h bar square into A by 2 must be equal to square root of 2m by h bar square u naught minus E 2m by h bar square E. Tan of root 2m E by h bar square A upon 2 must be equal to square root of u naught minus E minus 1. Okay, so what this is, everything is a constant here. A is the size of the wall, u naught is also size of the potential. So what this is basically this is an equation to determine the eigenenergy. Eigenenergy. All the various eigenenergies, possible eigenenergies, must satisfy this equation. Okay, they must satisfy this equation. If they don't satisfy this equation, then we are out of luck. They have to satisfy this equation. Okay, so this is how do you solve this equation? There's no way to solve this equation. Okay, because this equation is a transcendental equation. You have to solve it graphically. However, what we're going to do is solve it graphically, right? We're going to solve it graphically. How we solve it graphically? We're going to, on the x-axis. So what is our purpose here? Remember, our purpose is first to determine the eigenenergies, right? What are the possible eigenenergies? Once we determine a possible eigenenergy, then you can simply substitute here for E. Right, you can substitute. I can get the wave function basically. Right, that's what it is. And so you can plot the wave function after that. So we have to solve for this eigenenergy. So what I'm telling you is there are some values of E for which this equation is satisfied. There are other values of E for which this equation is not satisfied. Wherever this equation is not satisfied, that cannot be a possible eigenenergy for this particular system. Let us have a look at these numbers initially. Notice that E is always less than U naught. So U naught by E is always going to be greater than 1. And U naught by E is always going to be greater than 1. And so this number, second number on your left-hand side, is not going to be always positive, right? So that you have to take care. So I'm going to write it now in a very specific way. I'm going to redefine U naught by E as a new constant, little e. Maybe we should not use this particular term. Maybe we'll use some other term. Maybe we'll do little u. Okay. We'll simply redefine as a little u. So I can now write it as tan of square root of. So I can write E as U naught by U basically, right? So 2m by h bar square U naught upon little u. E is U naught by U. Yeah, that's correct. 2 naught U naught by little u into A over 2 is square root of U minus 1. Let us simplify this even further. We'll simplify this even further. Tan of square root of 2m U naught by h bar square A by 2 into 1 by root of u is equal to square root of E minus 1. So now, this entire thing will be some constant, right? So I can write it as tan of some x into x by root of u equal to root of u minus 1. And now our job is to solve for u here, right? How do we do that? We draw a graph basically. And I'll not solve exactly, but we'll just have an idea. So on the x-axis is u. And remember, u can never be, u naught by E can never be larger than 1, right? Because we don't want trapped energy to be larger than. So this u will only go from 0 to 1. Okay, we only need to do. Okay, so let's plot the left-hand side root of u minus 1. What will this look like? When u is 1, that means my E is exactly equal to u naught, right? When my u is 0, that means my energy is very, very small, basically. Because E is, oh, hold on, I think I'm making a mistake here. Yeah, when E is very small, I think I should define it the other way. I should define u as E by u naught. Okay. In that case, the maximum value that u will go is 0 to 1, right? And our equation will change slightly. So let's do that. Okay. So this will become 1 by u minus 1. And u can go from 0 to 1 at most. Yeah. And here, E is u times u naught. So the only thing that will change is, so this will, I'll have a U coming here. So I hope everybody is following this. Please let me know if something is not clear here. So this is your regular analytical physics, right? So yeah, something like this. And this left-hand side is 1 by U minus 1. And obviously, because I'm not that good, I make small mistakes. So, but luckily I correct them, right? So it's not too terrible. This is U. Right. So yeah, this is wrong actually. So now it's clear. U can only go from 0 to 1 because U is E by U naught, U by capital U naught. So of course my trapped energy can never be greater than, it can be 0 at it cannot be less than 0, and it can be greater than U naught. So little u can be only going from 0 to 1. It's clear, right? Right. So within that, let us look at the right hand side. So we'll basically plot this right hand curve. We'll also plot this left hand curve, and wherever they intersect, we know that those are the possible values for U, right? And those are the possible values for eigenenergy. Okay. So how does this function look like? I don't know, but we can guess, right? So if U is 0, then my function will be infinity, and when U is 1, then my function is 0. So how should it look like? It should look like 1 inverse 1 by x kind of function only. It should look something like that, where it exactly goes to 0 here. I don't know how exactly it will look, but I know, it's going to approximately look like 1 by x function only, except that it's not asymptotic. It's going to exactly go to 0 at this point, right? So I hope this is clear to you. Let's label that. This is your 1 by U minus 1 function, approximately. Okay. We don't care about, we don't want to know they plotted exactly, right? Why? Because computer is going to do that for us. Our purpose is here to establish how many possible, whether there is even a solution possible, and how many solutions are possible, and things like that. Okay. That's what we want to establish. Okay. Then we're going to look at the second, this particular guy, tan of x of root u. Okay. Now, when u is 0, where is this tan function? Is going to be 0 here, right? I'm going to use another color. It's going to be 0 here. And remember, tan functions do like that, right? They do something like that. They do something like that, where when the argument of the tan function goes to pi by 2. Okay, but it's going to start at 0. That is a great thing, right? So now here is a beautiful thing. Here's a beautiful thing. I know that this function, this whatever the functions on the left hand side, it's going to go to plus infinity somewhere, right? Maybe it won't go to 0 at 1. Maybe it goes at 20. Doesn't matter. It's wherever it does, I know for a fact that it's going to cross this curve at least once. Okay. That is the beauty, right? It's going to cross it at least once. Why is it crossing 1? Because this guy is going from infinity to 1, infinity to 0. This guy is going from 0 to infinity. So I know that they have to cross at least once. I know that they have to cross at least once before this point. Absolutely, it has to cross. There's no way it can cross afterwards. Right? So what is this telling me? It's telling me that one solution is guaranteed. One solution is absolutely guaranteed. Okay, that is all I wanted to prove, right? Where is the solution? What is the value? I don't care, doesn't matter, right? Now, depending on what this value of x is and how it's related to pi by 2, you may have multiple such crossings, right? So, in one situation, for example, you could have a situation like that, right? Now you have one solution, two solutions, three solutions, or you could have two solutions, but you can never have less than one solution. One solution is always guaranteed. Very profound, right? No matter how shallow your well is, no matter how small doesn't matter how small your unit is, no matter how small your mass is, doesn't matter, or how big it is, doesn't matter. Always, I'm going to have one solution. There is at least one solution is guaranteed. Okay. Now, what is the value of that? We cannot solve that analytically. This is something you have to go to a computer, substitute the values of U naught, H bar square, mass, everything. Solve this stupid equation. It's very hard, right? Using the computer numerically. Then only you'll be able to find the exact value. Wherever it intersects, you drop a perpendicular to that, you get some value of U. For example, maybe I got a value, this particular case could be 0.4. That means you now know that 0.4 is equal to E1 minus by U naught. So we know that E1 is 0.4 times U naught. Like this. This is how we solve the eigenenergies of the problem. And one eigenenergy is guaranteed. Now, if you go and do the same thing with the odd solution, then actually what you'll realize is there is no such guarantee. So for even solutions, one solution is guaranteed. For odd solutions, no guarantee. Okay, so you don't need. I mean, it's possible you could have it, but on the other hand, you need not also, right? So there's no guarantee. But okay. So this is. I hope this is clear. Let us actually. I'm going a little bit fast here because this is already very well known. Okay, so but I wanted to give you a nice perspective. So finite potential well, and it's going to be a good homework problem for you also. Finite potential well problem, right? So it's there in Wikipedia also. Very famous problem. So it does all this, right? Same like what I have done. Does the graphical solution. And realizes that these are the possible states and so on. Okay, so that is all from my side for this particular problem. Monica, I'm sure it's there in homework, right? So please have that. So there's other books as well you can always refer to. For example, this guy has done so they do solutions like this, right? So it's the same idea. Okay. All right, so that's that. It's a very quick idea of how this works out, right? But let us say I know the value of E now. That's how I find the eigenenergies, right? Let's say I found the eigenenergy value. Now the question is, how do I, what does the wave function look like? And the answer to that is what we're going to work on now. Remember, it's going to be of the form A, the even solutions at least, A cos kx. Just checking. Monica, is the screen visible? Hello?
Yes, sir, it is.
Okay, thanks. So this is for mod x is less than or equal to a by 2. And outside it's going to be e to the power proportional to, I'm just going to add the proportionality. Don't worry about the constants for now. Plus kappa x. And here's going to be e to the power minus kappa x. And we know that it's going to be continuous, right? How does this look like? These are all exponential tails. So there's sine in the middle, sine and cosine in the middle, exponential outside. So let's do that. So the very first one, E1 state, will be some cos k like that. Right? It's going to be something like that. And maybe let's draw the well on it, right? So here's my well. Okay. Here's my potential well. This is A by 2 plus A by 2 is minus A by 2. Okay. And let us say I found out some solution for E1. It's located here, right? This is your U0. How does the wave function look like? It's going to be, it's going to go to 0 here. So I'm going for drawing the wave function, I'm taking this E1 level as the 0, right? So it's going to do something like that. And then here in this portion, it's going to be a cos. Then again, it's going to do like that. Okay. Second one, what will it do? Second one will be exactly like this only. So it will be sine function like that. And then, it'll do something like that, right? Where this is the 0. Okay. So this exponential tail, because of the presence of this exponential tail, there is a small probability that I will be able to detect a trapped electron outside the well. Okay, but there is no flow, which means I'll not detect a constant flow. The electron is not flowing anywhere. Okay, I'll only detect its tail, basically. I'll detect the electron, but I will not detect, there's no flow of current as such because it is still trapped. Okay. All right. So I hope this idea is somewhat clear to you as to where this leakiness comes from. Great. So this is finishing our second idea, which is the finite well. Okay. Now, if you look at atoms, right? So atoms are potential wells in 3 dimensions, right? So if you understand this infinite potential well, then finite potential well, you should also understand, that if I have a infinite potential, the rate of decay, right? 2m root of u, this itself will go to infinite, basically. That's it. Kappa becomes infinite if my potential well is infinite. And so this tail will vanish, right? So that's what's happening. So because mathematically there two are very similar cases, right? Infinite well is nothing but u0 is infinity. So I showed you the continuity between the two. Great. So that is what will happen. I want to next go into something slightly. I don't want to go into 3 dimensions and atoms and so on. Well, let's leave that. It's interesting, but I hope you can get an idea now as to what will happen there, right? But we go into something slightly more interesting. Instead of having a one finite potential well, what if we have 2 potential wells like that? Now, this is a very interesting case, right? This is where we enter the ideas of molecules and so on. We have 2 potential wells like this. Now, what will happen? Now, it will turn out that if these wells are very far away, then, I'll have individual states like this, right? I'll have individual states like this. These wells are very far away. But what if those wells are very near? If those wells are very near, then these tail parts, which are there, those will start to interfere. Okay. And those will start to interfere. So let us think about what will happen, right? So imagine 2 wells here, very far away. Okay. And let us say I put two electrons in this system. What will happen? So what will be the total energy of the system, right? We'll solve the Schrodinger's equation in a very simple, in a single well only. We know that the ground state should be energy E1. So in the ground state of this particular 2 well system, total energy must be 2E1, right? That's what we expect. Anybody surprised? Not really, right? We'll simply, each electron in each well will be in the ground state. So its energy will be E1 and E1. Nothing surprising there. But when you bring them close together, there will be a surprise. And we'll not solve it now, but if you want, you can solve it. It's a little bit more involved. What will actually happen is, by the way, this is called a degeneracy. Okay. Why is it called degeneracy? It's called a degeneracy because I will have two electrons with the same energy, E1. Okay. So this kind of thing is called a degeneracy. It's energy degeneracy. It's very clear why there should be a degeneracy, right? Imagine that the two wells are isolated and they're very far away. There's hardly any interaction between them, right? There it's very easy to see that there's going to be a degeneracy. But it turns out that if you start bringing these walls close together, then these tail kind of things, right? These are going to interfere with each other. And yeah, and because it interferes, what will happen is that the electron will find a way. Both of these electrons will well, let me put it another way. Remember, all physical systems always try to go for the system with the lowest energy, right? So they will find another possible wave function whose energy is less than 2E1. Okay. How will they do that? They will do that by something called your bonding orbit. So the wave function will look different compared to this. In fact, the ground state wave function in a when these walls are very close together, I'm going to draw this. We're not deriving this, right? So I'm going to next draw the case where these walls are very close together. Okay. If this is the case, it turns out that your first wave function will be a bonding orbital. So it'll have something like that actually. So these two wave functions will merge together. And there is a higher probability of finding the electron in the middle of the wells rather than inside the well. And the second wave function will be this one, right? This will have this is called the anti-bonding orbit, or it's called the anti-bonding state. The first one is called the bonding state. So when you bring two walls together, both of them are not going to sit in. So one electron is going to sit in this level. Second electron is going to go sit here, basically. Okay. Ignoring spin. Let's ignore spin for now. If there is spin, then both electrons are going to sit. Then if there is spin, then we have one spin up electron, one spin down electron sitting like that. Okay. Here it was, there are random spins, right? Could be any random spin like that. But when I bring the walls closer together, how to intuitively see what is happening here? It's very simple. Imagine that there is a larger well like this. Okay. Then draw the very first state. Should have zero crossings, right? So that is why I know that the bonding state in the two well system, even without solving, I know it should have some function like this. And adding symmetry and so on, I know it should look exactly like this. Okay. You can also do this now, right? So remember, we're not solving Schrodinger's equation, but we are using our physical intuition about symmetry, intuition about from the zero crossing theorem. And I'm thinking of these two well as like one separate well. And then based on that, you can draw how the bonding state looks like, anti-bonding state looks like, and so on. Okay. So this is what happens. You had a bonding state formed. You can extrapolate this idea even further. Okay, this is where the really cool thing starts to happen. So now let's go from one well, and from two wells, let's imagine a three-well system. What would happen in a three-well system? Well, I don't know, right? It's too complicated to solve, but I don't care. I'm going to use my knowledge, and I'm going to come and tell you that. Okay, the wave first state should look almost like that, and the second should look almost like that. So this is your orbital, second orbital, and so on. Okay, so yeah, so you can take this extrapolation like this. So different kinds of possible. And where have we seen this? This is your chemistry, right? This is your hydrogen molecule. What is this? This is your 3 atom. This could be H2 or something like that, right? So you have all your. Now you can imagine all of chemistry in terms of what we know about uh, finite potential wells and the zero crossing theorem, right?
Uh,
Yeah.
Sir, in case of 3 wells, if there
Yeah.
are 3 electrons, then there
There
should
will
be
be
three
three.
states, right?
There will be three degeneracy, right? Three E energy degeneracy, and because when we
Okay.
bring them close together, that energy will be lifted, and I'll get three separate energy levels.
Okay.
Okay, there will be a three energy split.
Out of curiosity.
Huh?
Okay. Sir, I have a question.
Sorry, I cannot hear you well. Your voice is getting cut off. No, I cannot hear you. Your voice is getting cut off, Snehal. Can anybody else hear him? I cannot hear him. Can anybody else hear what he's saying?
His voice is cracking. Maybe Snail, you can type your problem in the chat.
Yeah, please do that. I because I cannot hear you. So imagine this, right? So let us take one finite well, okay, and I'm going to draw the. If I solve it in isolation, it's have its energy E1, E2, and so on, right? Now you start bringing multiple wells together. If I bring two wells together, how does the energy eigenvalue spectrum look for this? It's going to be, I'll draw E1, but the final answer will be one energy slightly larger than E1, one energy slightly smaller than E1. So this is called a degeneracy split. Degeneracy split. So if I have three, you'll have a three split. Okay. In the three split, what will happen is one, yeah, I guess that was the question, right? So if this is E1, in a two split, the anti-bonding will have slightly larger energy than E1. The bonding will have a slightly lower energy than. This is a two split. Now, I guess this was your question, Mandal. This is your E1. How will a three split happen, right? So three split will happen like this. 1, 2, 3. One will overlap with E1. Okay, this is your three split. And how far will they split? That's another question, right? The closer you bring them, the higher the value of the split. Okay, so things that are very, very close will have a very large split. And if they're very far away, that is understood, right? See, imagine if I have in two atoms very far away, then their energy will almost, both of them will be E1 only. No? So we know that the farther away, the lower the split. Nearer, higher the split, right? So now imagine, is he there? Did he type his question? Okay, he has his question here. Okay. Yeah, okay, he's going to type, I guess, yeah. So this is, right? So let's take this. Yes, sir. Yeah, you're back.
Sir, am I audible now?
Yeah, you're audible now. Yes, sir. Go ahead.
Sir, I was just asking that. Suppose I have two states which are far apart, and the total energy, as you said, was 2E1.
No. You're using wrong terminology. Two wells that are not states.
Right. Sorry, sir. There are two wells, and each have an energy E1. So total energy was 2E1. So now,
No, again, terminology, you have to be very specific. Each have a ground state eigenvalue of E1, right?
Right.
Say
Okay.
identical wells, two identical wells far away.
Yes, sir.
Great,
And
okay.
the ground state energy is 2E1.
For the combined system.
For the combined, right. So
Yes.
now when the two wells are approaching and as at a very close distance,
right,
then there will be an anti-bonding state and a bonding state.
And a bonding state, yes.
So if I calculate their energy, so will the sum be equal to 2E1?
No, it will be less than 2e1. If it was not, then there is no reason for the bonding orbital to arise in the first place, right?
Okay.
See, yeah, very nice question. I think I'll clarify. I got your question, right? It's a good question. So, yeah. So the answer to this partly has to do with spin. Okay. You have to consider spin to answer your question. If you don't consider spin, then this will not make sense. So let's consider spin. So let's imagine very carefully. So we have this system. Okay. And assume that there are 2 electrons in each well. Then this will become clear to you. Okay. Sorry, assume there are 1, not 2. My mistake. Yeah. Okay, this is E1. Up spin. This is one hydrogen atom, this is one hydrogen atom. Okay, very simple. So I bring them close together and I put them very close together. Now what will happen? Now this combined system will have its own energy, E combined 1, right? It will have its own second energy, E combined 2. This E combined 1 will be less than E1. E combined 2 will be larger than E1. And so E1, our original E1 is going to lie somewhere in between these two. Now, because of Pauli exclusion principle, what will happen is how will the electrons fill this? One electron will do like that, another electron will do like that. So here my total energy was 2E1, right? What is the total energy here? It is 2EC1, which is less than 2E1. Is that clear?
Okay, so sir, none of the electrons will go to E2C.
No, because otherwise there is no, you haven't minimized energy now.
Oh.
See, yeah, this is your hydrogen molecule. Because I have minimized the total energy, that is why this is a favored state. That's why you have 2 hydrogen gases floating around, they'll form a hydrogen molecule. Because by doing that, they're going to minimize the total energy of the system. Is that clear?
Yes, sir.
It's very nice, right? So, maybe I don't think you have ever thought of chemistry in this way, but that's exactly what it is.
Thank you.
One thing.
Yes, sir.
Sir, why here is like a 2 split energy? If both are combined, then maybe only 1 energy level.
Nahi hoga na. I'll tell you why. See, yeah, that's another good question. See, so this is your well, ठीक है? तो इसका हम जब Schrodinger solution करेंगे, तो इसका आपका पहले E1 आएगा, E2 आएगा, ऐसा होगा ना? Now imagine a well like this. Now imagine a slightly different well like this. ऐसा well एक imagine करो. जिसमें it is almost like this well only, but there is a bump in the middle. Okay, are you getting the idea?
Yes, sir.
है ना? तो इसमें जब हम Schrodinger solve करेंगे, in fact, maybe I'll write it in this way, right? Maybe I'll have the same dimension also, so as not to confuse you. So imagine a well now, which is exactly same like this, except there is a very sharp bump in the middle. So they are almost identical, right? So here when we solve the Schrodinger's equation, I'll have some E1, some E2. Okay, are you following until now?
Yes, sir.
So now imagine your 2 wells, right? 2 wells like this. You can imagine that this is like a composite well. And it will have its own states. Okay. And because this is wider, this well is wider than this well, the lowest energy state of this combined well is going to be smaller than E1.
Yes, sir.
Do you see the see what is happening now?
Yes, sir.
Yes?
Yes, sir.
Okay. Any other question?
Thank you.
Thank you. These are very subtle points, right? But they're very intuitive, right? You have to understand why that's happening. If I have a 2 well system, if you bring them very close together, it will start looking like one well only with some weird potential. That's all. right? And because it's a well with a weird potential, we know our zero crossing theorem, right? I know that the first state must be without, must not have any crossing, zero crossing. Second state must have one zero crossing. And so I know that for this combined system, na, iska jo pehla state rahega, that will look something like this only. Second one will look like this only. That much I know. Then if you ask me, when I solve it, what will be the eigen value of this particular state? I'll say, I don't know exactly, but I know that this second well that I'm solving, this strange shaped well, it is wider than it's wider than our original well, right? And now look at it. When we are doing this solution here, right? When you're doing this solution here, see, everything is scaled by the width of the well. See, A is here, right? See, A is here. So if my A is larger, then wherever this tan curve will cross, that will cross slightly away from this. Okay, it'll cross. Sorry, not away. It'll cross before only. So it'll cross before. So based on that, you can see that E1 will E1 for this larger well will be lower. You can also see this in the equation for our infinite potential well, right? What was the energy? N square H square by 2A was there, right? 2m d squared was here. N square pi square. So d was in the denominator. So the wider the well, the lower the value of that energy. So that is exactly what is happening here. When I bring the two wells very close together, they act like one slightly bigger super well. And that super well will have a lower energy. And because of the spin states, two of these electrons can now occupy that lower level. And so they have minimized the total energy. Because they have minimized the total energy, this particular configuration is more favored than the individual configuration. Okay. Maybe I'm giving you more information than you bargained for, but it's very important that you realize this, right? That you're able to understand it at this level. So let us go further now that you understand the two things carefully. What happens if I start increasing the number of wells? What if I put more and more wells together, right? So this same idea should hold there also. So if I had one well, its energy was E1 here, E2 here, E3 like this, right? Finite well. Now this E1 will split. In fact, it will split into a band. E2 will also become a band. E3 will also become a band. Inside this band, there will be levels, they'll be very close together. They'll be very close together. Okay. And the distance between these individual levels is again decided by how close the wells are. If the wells are very close, then these E1, E2 itself will be far apart, right? And so the gap between this and this will be larger if the lattice, which the distance between these is called the lattice. If that is smaller, then the difference between E2 and E1 itself will be larger, which means this is your band gap. Ye apna band gap. Ye apna crystal ho gaya already now. So you see, I took the understanding what we had developed from a finite potential well, and I then talked about splitting. Then I increased that splitting and I said, okay, now consider a very large number of coupled wells together. And when we do that, we emerge on the concept of bands. So this is your valence band, this is your conduction band, this is some higher order band. And you have a band gap and all these ideas start coming in. Okay. There is little bit more subtlety to this than this, but essentially this itself is the idea. This is all there is to it. Okay. This is exactly what's going on, especially for, right, especially for topmost electrons. This is exactly the picture. Okay, any questions on this? Am I being clear? Any questions on this?
Sir,
Are
may I
you- Yes,
doubt
sir.
here?
Hmm.
Sir, when we are bringing two wells together, we
Yes,
can see that, okay, we have an anti-bonding state and a bonding state, right?
right.
And we have said that in bonding state, the two electrons will lie with the opposite spin.
Yes.
But sir, when we have studied that how the silicon crystal is forming, like there are four electrons of a silicon in the outermost shell. Now,
Hmm.
when n silicon atoms are coming closer, so
Hmm.
we see that there are total 8n states. Out of that
Hmm.
8n states, 4n are filled, which are valence band, and
Hmm.
4n are empty, which are conduction band. Right?
No. I think you are. No. See, first of all, when your silicon, if I bring one silicon, it will form bonds with 4 other silicon atoms, right? So to complete that 8, basically. है ना? So those are filled, right? Those are not empty. Those are tightly filled. There's nothing empty there.
Yes. But
It's
sir,
filled together. No, bonds are filled. Their bonds are filled. There's nothing empty there. There's no conduction band at that point, right? Because they're all sitting in the valence band only.
yes, but the band will be there, na?
Band will be there. Okay.
So what I'm saying is that if I bring n electrons,
Huh.
n silicon atoms, then there will be 4n valence band and 4n conduction band, which are completely empty, and the valence is filled, right?
No. You're okay. See, you're. There are many confusions here. Let me clear them one by one. Okay. So, see, individual silicon will have levels something like that, right? So most of these lower levels will be already filled by the inner electrons. So this is your valence, for example. So now we are looking at only two of these bands, basically. Okay. So see, you got it now.
Yes, sir.
You're looking at all. See, you're looking at every electron. Now, silicon has so many electrons. Don't look at all of them. Only look at the very topmost where it's entirely full, and where the next band is there, which is entirely empty.
Okay.
Okay.
Yes,
We'll worry about crystals a little bit later. Okay, but think about it. I think this is your confusion.
Okay, sir. I will look into and let you know.
Think about it. Okay, because see, I mean, there are many things you are getting confused with. So first of all, so silicon, you can think about it like this. Everything below is already full, right? So maybe this one is empty like this, right? Okay. Are you getting what I'm saying here?
Yes, sir.
So what will happen now is this level will split like this. This level is split into a band. Okay. Now there is a higher band like this here. So this level will be completely filled with electron. This will be fully empty. This is your valence band. This is your conduction. All these electrons are not participating. They're not interesting.
So can I comment that conduction band?
Last electron was there, na? Whichever electron was, all these 4 electrons were there. They're all in one same degeneracy. There is a degeneracy there. They form sp3 hybridization. Okay, and it has imagine them all to be in the same level only. So all of those give rise to one band. All those extra last electron is there, na? They're all going to because they're degenerate. Okay, they're degenerate, and they will all at the end of the day they're going to give rise to one particular band, right? And then the next level is there, na? That will give rise to the next band. So this whatever band was given by this one, that becomes your valence band. So next empty level becomes a conduction band.
Okay, sir.
Okay. Any other question? Okay. So yeah. anyway, we will look at the crystal formation in detail later on also. So not to worry too much. But what I wanted to tell you is that the idea of this potential well is very powerful, right? So from there only, you get all your concepts of band formation and everything. So okay, so I'll catch this up again on Friday. Monica, I think it's time for first homework, right?
Yes, sir. I'll post the questions there.
Yeah,
Class.
Monica. So yeah, it should be similar. It can be similar to what we did last time only. So it's going to come from the quantum mechanics chapter. Give some handwritten exercises, maybe one programming exercise with the finite potential well, and I guess one problem we can have with the tunneling as well.
Okay, sure, sir. Sir, the time for this would be 2 weeks, right? For one
Yeah,
assignment.
we'll have a 2 weeks time. Yeah, exactly.
Okay, sure, sir.
Okay, so yeah, we'll announce this. You prepare it, and we'll try to announce it. We'll try to post it by Friday, this Friday, and then after 2 weeks from now, it will be.
Okay, sir. Okay, sir.
Okay, so I think you are now ready to solve some quantum mechanics problems on your own, using manipulating wave functions and such. So that's what the first homework will deal with. Okay, so if you are having a little bit uncomfortable, go through the videos once again, and try to work it out by hand by yourself, and I'm sure you'll get it. If you have any problems, do let us know. Okay, so anything else before I close? Okay, so Monica, this Friday also we are doing offline only. Then is next week okay? Should we do online? What is your suggestion? Or can we continue offline only? Because there are so many cases.
Sir, I'm in support of online classes.
Okay. Anybody in objection to offline classes? I mean, no, right? I'm sure you're all really dying to interact with me on a classroom basis, but you know what? I think let's better be safe, right? So yeah, let's continue online, guys. I don't. It's left to the discretion of the instructor. So I am discreting to stick around and online only. Any objections? No objections, right?
No, sir, but in offline, the learning becomes slightly better. So
Oh yeah, that is true.
but COVID is also rising, so I don't know, sir.
Okay.
At least 1 week is online. We can continue online.
ठीक है, next week next week भी online करते हैं, उसके बाद open कर देते हैं फिर.
Yes, sir.
All right, thank you everybody. Thank you, bye.
Sir, one more thing, sir.
हाँ sir.
सर जो क्लास नोट्स जो जैसे आप क्लास नोट करते हो उसका पीडीएफ सर अपलोड हो जाता तो ज्यादा बेटर रहता सर.
ठीक है, आपको चाहिए तो मैं कर देता हूँ, नो प्रॉब्लम.
हाँ ठीक है सर, वो प्रीवियस क्लासेज का भी अगर हो पाए.
No problem. It's all there in just one PDF only. Everything is there in
yes,
one PDF. So I'll email it to Monica. She'll share it with you.
Yes, sir. Thank you.
Okay, thank you guys. Thank you.